by 2 pi epsilon naught r and I hat, if we are looking in this direction, right?
Okay.
Right? And
Yes.
yeah, and then this part, this y part is Ey, and this is 0, right? So we have only one electric field that is in this direction, or in this direction, this would be in this direction, right? So this is the result that we have to remember. And yeah, just simply we have to remember that electric field, we can remove this part, and this is 2 pi epsilon naught r. Right. This is the derivation. This is not the, this is the result. So derivation, you look at it, and if you have any doubt, please ask me. So this would be
Yes,
the
sir.
correct, right? Right.
Yes,
Okay.
sir.
So now using this idea, right? Using this idea, we have this question. Two parallel infinite line charges, right, with linear charge density lambda and minus lambda are placed at a distance of 2r in free space, right? So we have to remember this thing only, right? And there are two line charges. So one is this one, and this is infinite, right? Again, another one, this is infinite. But the tagline is that this one is positive lambda, this one is minus lambda, right? So these are the two charge distributions are placed at a distance of 2r. So the distance or separation between them is 2r, right? Now, what is the electric field midway between the two line charges, right? So where do we have to calculate the electric field?
In the middle.
In the middle, right? In the midpoint. So this is the point at which we have to calculate the electric field. How many contribution would be there at this point?
I guess from minus lambda and then positive lambda
Yeah,
from there.
two contributions. So two line
Yeah.
charges, right? So two contribution.
Yes.
Due to this one, right? Due to this one, what would be the direction of the electric field? Due to this one at this point.
It would be attractive, right?
This is positive, right? So
Mm. Because there's a negative lambda, so that will also come, right?
yeah. So due to this one, the electric field would be in this direction, right?
Yeah, towards negative lambda.
Yeah, and due to this one, right? Due to this wire, the electric field would be in which direction?
Guess it'll
No.
be outside.
Which side? Again, the same side, right?
Yeah, the same side.
Because this is minus, so this would be attractive. This would be
Mm.
repulsive, right? So
Yeah,
we have two electric field in the same direction, and the direction is what? Can you tell me what is the direction?
towards negative lambda.
I had, right?
Oh, okay. Yeah, I had.
Yeah, so this is the right, because you see the options, right? They have I. So
Oh,
all the options are I. So we have to write I, right? Now, what would be E1? Can you tell me? Let me write the vector form. So what would be E1? You have to just remember this thing, right?
yes.
So what would be E1?
E1 will be positive lambda by 2 pi epsilon r, and then
And
will
I had.
be I cap.
Yeah. And remember, we have already taken the direction. So we don't write positive, negative lambda, right? We only
Okay.
write lambda, right? Because if we write the negative lambda, then we have to write this minus I hat. So then that would be again positive. So we have
Yeah.
already taken the negative nature, right? So yeah, so again, E2 would be lambda by 2 pi epsilon naught and I. Is it correct?
Yes.
Yeah, because both are in the same direction. Magnitude is this one, right?
Hmm.
This is the magnitude, and direction is both have a direction I. So magnitude into direction, right? That is the vector. Okay, now we have to calculate the net electric field. So net electric field is simply superposition, right? And then this would be lambda by 2 pi epsilon naught r I hat and C. So this would be 2 lambda by 2 pi epsilon naught r. I hat 2 cancels, and this is lambda by pi epsilon naught r. So this is E, right?
Yes.
So this option is correct. Please note it down, and if you have any doubt, please tell me.
Okay, sir.
Yeah, now write down the question first and then the answer, right?
Yes. Done, sir.
Done. Okay, so then this electric field due to linear wire is also done. The circular part is not in the syllabus for CBSE, right? So we skip that. And then we have, yeah. So then all the electric field portion is done, right?
Okay, sir.
So we calculated electric field for point charge. We calculated electric field for multiple charges. We calculated electric field for dipole, and we calculated the electric field for this linear charge wire, right? And
Yes, sir.
using the Gauss law, we learned that we have electric field due to a sheet, and then electric field due to a cylindrical wire. So all those things we will do, right? Okay, so
But
now the
in
next
a
part, yeah.
school, spherical shell was also taught.
Which what?
The spherical shell, the Gauss law.
Yeah, yeah. Oh, yeah, yeah, yeah. In Gauss law, you have this, yeah. So this shell, right? And the electric
Yeah.
field varies like this one. So this part is zero, and then it varies like this, right?
Hmm.
Yeah. So this we have to also do. Yes, correct. Okay. So yeah. So the next topic is electric field lines, right? And those are, yeah, so those things you already know, right? That the tangent to the electric field lines will give you the direction of the electric field. They can't be intersecting, and it goes out from the positive and comes out to the negative. And yeah, all those things about the electric field lines you already know, right?
Yes,
So
sir.
so we can skip that. And yeah, and the next question or the next topic that comes from this part is the that is electric field charge on a particle, force particle or force on a charge in presence of electric field, right? So this is the next topic that you have learned. Yeah. And there are mainly two questions we use to show this thing, right? So what is the theory? That let's say if we have this electric field, and this electric field is uniform, right? So that is the so whenever we want to show the uniform electric field, how do we show that? How do we show that the electric field is uniform? So we show that by writing these parallel lines, right?
Yes.
And they have the same separation, right? If the separation is different, then the field is not uniform, right?
Hmm.
Yeah, so this is the electric field, which is uniform, right? Now we put some charge in here, let's say at this point, right? So then the force on this charge would simply be in this direction, right? And this would be equal to Q, right? That we understand, right?
Yes.
And let's say if we put a negative charge, then what would be the direction of force?
DT opposite.
Opposite, absolutely correct. So that would be in the opposite direction of the electric field, right? So this would be in the opposite direction. So these are the two things we have to remember, right? If we have negative charge, force would be in opposite direction. If we have a positive charge, force would be in the same direction as electric field. So what is the question, right? What is the question that is asked in these kind of scenarios, right? So question is that, let's say you are putting a charge in the air, which has some mass m and charge q. Or let's say that, yeah, so it has some charge q, charge q having, and this is positive, right? Having mass m is put in the air, which is stationary, which is in the presence of, or which is stationary, right? Find the direction and magnitude of electric field to put it in the air. Right. So what do we have? We have this earth, right? So this is the surface, and we are putting a charge in the air. Let's say here, this is plus Q charge, right? So if there is no electric field, what is the force that is acting on this thing?
Gravitational force.
Gravitational force. So it will be attracted downwards, right?
Yes.
Now we want to balance this. Charge, right? So we need to have an electric field in which direction? Or we need to have a force in which direction? That is a wrong question. We need to have a force in which direction?
Upwards.
Upward, right? So we need to have a balancing force upward direction, right? And that force can be provided by what? That electric field, right? External
Yes.
electric field. So now you see that this is a positive charge, right? We
Hmm.
require a force in the upward direction. So which means that we require an electric field, right? For positive charge, the electric field has the same direction as force, right?
Yes.
So we need an electric field in this direction, right? Right?
Yes.
So now we know that the electric field direction would be upwards. This one part is clear. Now, what would be the magnitude of this thing? So we know that these two are balancing, right? These two are at equilibrium, right? Let's say point P. So point P at equilibrium, which means what? Both the forces are balancing, right?
Equal.
Yeah, they are equal. So F of, let's say, electric field, this would be equal to this mg, right? So this is simply QE. So E would be simply mg by Q. So this much amount of electric field we have to provide. Clear?
Yes, sir.
And let's say that if you have a negative charge, then what would happen? Can you tell me, if you have a negative charge, right? And this is mg. So what kind of electric field, or what direction of electric field we require? Can you tell me?
It would be downwards electric field.
Yeah, absolutely correct, because the force is again upwards, right?
Hmm.
And this is a negative charge. For negative charge, the electric field in opposite direction. So we have
Yeah.
an electric field which is in opposite direction, right? Good. So this is the electric field. Yeah, and the magnitude would be same, right? Magnitude would be
Hmm.
this one. Okay, so good. Please note down this question, and then we will talk about another question, right? Okay, have you started that third chapter?
Yes, sir. Sir, can you please scroll down?
Yeah.
Done.
Yeah. Okay, so now let us do another kind of question, and that is related with right. So the question is in the form of this. So you have a tunnel, right? And it has an electric field, let's say, in this direction. So this is positive. This is negative. So electric field in this direction, right? And then this distance is D. This distance is L, right? Now, there are two particles which are given some velocity, right? With the same velocity. They are given the same velocity. And let's say that one is proton, right? Proton is here, right? And it is given some velocity u. This is proton, right? And now, because you have this electric field in this direction, so this proton will feel the force, right?
Yes.
So this proton will, give me one moment, give me one. Okay, yeah. So proton will feel the force in this direction, right? Now, what would be the amount of the force? Force would be simply QE, right?
Yes.
And this E is uniform, right? This E is uniform. So if we write the magnitude, this is Q, this is E. And now we know that the force, because this is moving, this proton is moving, so it will have some acceleration, right? So this is, let's say this is MP. So acceleration would be how much? That would be QE by MP, right?
Hmm.
Now, what kind of acceleration is this one? What kind of acceleration? Is this a uniform acceleration or it is a non-uniform acceleration? What kind of acceleration is this one?
Non-uniform.
Non-uniform. Q is a constant or varying. What is Q?
The value.
It
Uh,
is constant, right? Charge on proton.
Yeah,
That is
yeah.
E.
Okay,
So
yeah,
that
yeah.
is,
In terms of, yeah,
yeah, so
proton.
this is E and MP, right? So this is the acceleration. So this is
Hmm.
constant, right? E is
Hmm.
constant or changing.
It can change.
It is uniform, right? It is
Hmm.
also constant, right? And mass of the
Okay.
proton, that is also constant, right?
Understand.
So which means
Yeah.
that this acceleration is uniform,
Okay.
right? And whenever we have a uniform acceleration, then what we can apply? For uniform acceleration, we have kinematics equation, right?
Hmm.
X equation because A is uniform. And if we write it precisely, right? If we write it precisely, so this A is in the direction of, let's say, AY. AY is A and AX is 0, right? No acceleration in the right direction. We have only acceleration in the upward direction, right? Clear?
Yes.
Now, similar thing we do. So now we provide an electron from this side, right? So electron will feel the force in which direction? This is the electric field, right?
Hmm.
So electron, let's say we provide again, this is electron. And we provide u velocity. So for this electron, the force would be in this downward direction, right?
Yes.
So the trajectory of electron would be, because, yeah, so trajectory of proton would be this one, right? Because it is feeling
Hmm.
a force in the upward direction. Trajectory of electron
Yes.
would be this, right?
Yes.
So we have the question is that who will cross first, right? Who will cross this tunnel first? That is the question. Is it clear?
Yes.
Yeah, so we have to find out TE or TE and TP. Which one is greater? Right. So let us find that out. So we know that, right? We know that this is moving in one dimension or two dimension. This thing is moving in one dimension or two dimension.
Two dimension.
Two dimension, right? So it will have X component
Y.
and Y component, right? So X component would be what? This would be V x square, or let me write Vx, that would be Ux plus At, right? Or Axt. And then the other would be x equal to uxt plus half axt square, right? And then third
Yes.
one would be vx square minus ux square is 2x or axx, right? So these are the three equations, kinematics equations. Similarly, we can write the y part. So y part would be vy equals to uy plus ayt, right? And then this thing would be y equals to uyt plus half ayt square. And then third one is vy square minus uy square, that is 2ayy. So these are the three things, right?
Yes.
What are the known things that we have? Let us write the known things. What are the known things? Can you tell me? Known thing is that ux is u, uy is 0, right?
Yes.
And also you have x equals to L and y equal to D, right?
Mm.
And also you have ax equal to 0 and ay equal to this e by m, right? These are the known quantities that we have. Clear?
Yes, sir.
Okay. So now let us solve this question, right? So now we can solve this question. So we want to calculate this t, right? So we know this y and we know uy, we know all these things. So we can calculate using this thing, right? Right?
Yes.
So let us, or we can use this x1 also, right? We know x, we know L, and all those things we know. But mass is not, because we want to relate it with electron and proton, right?
Mm.
Electron and proton contribution is coming from mass, right?
Yes.
So because if we calculate the x component, we will only have u. Ax is 0. So whatever acceleration we have, right? If we are providing the same velocity, so they will take the same time to cover these distances, right? So yeah, so let us only consider the y component. Now we consider the second part of the y component. So y is uyt plus half ayt square. Y is how much? That is d, right?
Yes.
Uy is 0, so that part is cancelled. And half ay we have already calculated. So ay was how much? E,
E into
e
E
by
by
m,
M.
right? And t
Mm.
square. So if we calculate t square, right, this would be, or let me write it first. So this d is half e t square by m. So if we calculate time, because the unknown that we have to calculate is time, right?
Mm.
So let us calculate this thing. So t square is 2dm, right? And then divided by
E.
right? So
Mhm.
t would be
Under root
simply
of.
dm by e. So you see that this d is constant, right?
Yes.
This E is constant, this electric field is constant. And if we
Hmm.
take the different masses, so only mass is changing, right?
Yes.
So T is directly proportional to root M. Am I correct or not? Because D, E, and E are fixed, right? They are constant. Only we are
Yes.
having electron and proton, so only mass is changing. So if,
Hmm.
right, if we know that mass of proton is heavier or lighter than electron. Which one is greater?
Mass
Which
of
one?
proton.
Mass of proton is greater, right? So this is greater than this, right? This we know.
Yes.
Now let's say that time taken by electron, this would be proportional to this root of ME, right?
Hmm.
And time of proton, that would be proportional to time of ME, right? Now
Hmm.
what we do is that we divide TP by T. So this proportionality will be removed, right? And this would be root of MP divided by root of N, right? So this would be root of MP by ME, right?
Yes.
Now, so what would be this quantity? We know that MP is greater than this thing. So if we take ME in this side, right? So what we will have in the other side? If we take ME from this side, what will be there remaining?
T P by T.
No, no. So we have taken ME in this side. We have this relation, right? So let's say
Hmm.
you have X equal X is greater than Y, right? You take this Y the other side, X by Y. So what is remaining in this place? 1,
1.
right? Yeah. So this would be 1. So MP by ME is greater than 1, right? We can
Okay.
put that value, yeah, we can put that value in here. So this would be greater than 1, and we can write that thing, right? So we can write that thing as greater than 1, right?
Yes.
Clear? So then we can write that proton will take larger time to cross this thing. Clear?
Hmm.
So electron will move quickly, and proton will take a larger time to cross this term. So that is the answer, right? Oh, did we? Yeah, so this is correct. Okay, so is this question clear to you?
Yes, sir.
Yeah, this one question is very important in context of CBSE, right? So yeah, please note it down, and if you have any doubt, please tell.
Okay, sir.
Then we'll talk about the torque experienced by the dipole, right, in the presence of the electric field. Yeah, whenever you want me to scroll down, please tell me.
Okay. So can you please scroll down?
Yes, yes.
Done, sir.
Yeah. Okay, so now this topic is also done. So now the next topic is torque, right? Torque on an electric dipole in external electric field, right? So, like, so what is the torque? So we already know, right? This you have already derived. So you have again an electric field, right? And this time you are not placing a unit charge or a particle charge, right? You are placing a dipole. Let's say this is the dipole, right? So this has minus Q and this is Q. So this is the dipole that you are placing, right? And it has a separation 2A. So now we already know that this one will feel the force in this direction and this one will feel the force in this direction, right? Amount of the force, magnitude of the force would be equal, right? But so if the forces are equal, so you have right hand side force equal, left hand side force equal. So this would be a translation equilibrium, right? Translation equilibrium, why? Because you have this F left equals to F right, right?
Yes.
Now because this is creating a couple, right? So this is the line of action. This is the line of action for this force. This is the line of the action for this force. So now they will create a couple, right? And what would be the couple? So this is the distance between them, right? And this angle is theta, right? So what would be this distance? So couple, which is the torque, right? So couple is what? This is the force into the perpendicular distance, right?
Yeah.
R perpendicular. So this is the R perpendicular between the line of action, right?
Mm.
So we know that this is 2A, this is theta, this is hypotenuse, this is perpendicular. What relates perpendicular and hypotenuse? What relates that?
Sine theta.
Sine theta, right? So if we calculate sine theta, this would be perpendicular by hypotenuse, right? So
Mm.
R perpendicular would be 2A sine theta, right?
Yes.
So if we write that thing in here, so this would be F and 2A sine theta, right? And what would be the amount of this force? That would be simply QE, right?
Mm.
So can you identify what is this 2AQ? What is this 2AQ?
G.
Separation into charge. What is this
Yeah.
thing? Dipole moment, right?
Dipole moment. Okay.
So PE sine theta, right?
Yeah.
Right? And
Mm.
if we remember the cross product, so this is what? This is what?
E
PE sine theta.
cross E.
Yeah, so this is P cross E, right? So then we can write the torque as P cross E. So this is the torque experienced by the dipole in the presence of the electric field, right? And there are three conditions, right? What are those conditions? So depending upon theta, right? Depending on theta. special conditions. This is a general one, right? This one is a, but we have three special conditions or three special, what do you say? So scenarios, right? First one is that you have this dipole. I will not make a bigger diagram this time. You have this electric field uniform, and you put your dipole in this way. What is the angle in here? Oh, who got disconnected? What is the angle in here?
0 degree.
You see, this is P, right?
Oh, 180 degree.
This is E.
Okay, okay. So
Yeah,
it's
so this is
90 degree.
90 degree, yes. So this is 90 degree, right? So we have to calculate the angle between P and E, right? So theta is 90 degree, right? And then what would be torque? So torque would be PE sine theta. Theta is 90,
So
right? So this
PE.
is sine. Yeah, so this would be PE, which
PE.
is maximum, right? So the maximum torque will be experienced at this point, right?
Yes.
Okay, and then the second condition is that you are placing this dipole in this manner. So let's say you put it minus Q and then Q. So what is the angle now?
It's like on the same line. So 0
Yeah,
degree.
if I can draw it in here also. So yeah, same line we can say, but yeah, so 0 degree because P is in this direction, right? Negative to positive. And
And E
electric field
is
is
also
also in this direction.
same
So
direction.
theta is 0 degree, right? So then this torque would be PE
0.
again sine theta, and this would be 0. So there is no rotational effect, right? So this would be called equilibrium. But
Equilibrium.
right, but this would be called a stable equilibrium, right? So this is a stable equilibrium. Why we are calling it a stable equilibrium? Because if we displace this thing, right? So this is the idea of a stable equilibrium. You have this point, right? If you take
Yes.
this mass, place it in here, right? So what it will do? It will again roll, right? And it will oscillate and it will come back to its initial position, right?
Yes.
So this is what we call the stable equilibrium, right? Now the last special case is this one. So you have an electric field, right? Let us draw a few diagrams. And then you place the dipole in this manner. So what is the angle now?
180 degree because
180 degree,
opposite
yes.
direction.
Yeah, this is P, right? And this is E. So theta has become 180 degree. So now your tau would be again PE sine theta, right? This is again PE sine 180. So sine 180 is how much? That is 0.
0.
So again we have equilibrium, right? Again we have equilibrium, but this is called unstable.
Unstable.
Why unstable? Because this behaves like this one. So this point, right? If you don't touch this point, so this will remain in here, right? And if I displace this thing, Let's say if I displace this thing in here, so it will go down, right? It will not come back to its initial state. Clear?
Yes,
So
sir.
this equilibrium is unstable. So this was about the talk on D dipole, right? Please note it down, and then we'll start flux, electric flux, last topic, right?
Okay, sir. Can you scroll down?
Yeah.
Done.
Then this one also done.
Yeah, I wrote.
Okay, good. So now the last topic of this chapter, right? And then we'll start the second chapter. So this one is the biggest chapter, right? And it takes time. So the last topic is electric flux and Gauss, all right? So what do we have in this one? So I will, because you have already done all these things, so we'll only do the important part, right? So we know that what is the electric flux, right? We have distribution, surface charge distribution, right? And then this has some area, right? So what would be the direction of area vector for this surface?
I don't get it. Like,
Yeah, so let's say you have this surface. Yeah, this is the surface. Let's say you have a table. So table
Hmm.
has an area, right? And
Hmm.
area is a vector quantity. So if we take the direction of the area vector, what is the direction of the area vector?
Like I cap and K cap because it's in the Z and X direction.
Okay, so that is always normal to the surface, right?
Okay.
Yeah, this is the direction of the area vector, always normal. So for this one, this is the area vector, right? In this case, this is I hat, as you were saying. In this case, it is J hat, right?
Hmm.
So this is the direction of the area vector. Now, yeah, because this has this area, let's say A, right? This has, let's say, area A. Now, this is a plane surface, right? This surface is a plane surface, right?
Yes.
What would happen if we have a surface which is something like this one, right? So you see that the direction of area vector will always be changing, right? Right.
Yes.
So for this surface, whenever we have a curved surface, this is a curved surface, right? For this, and this is a plane surface, right? So for plane surface, we directly take flux to be simply E dot A, right? Because area vector has only one direction, right?
Hmm.
But for curved surface, what do we do? For curved surface, we consider a small surface element, ds, right? And then we integrate this thing. So for curved surface, what do we do is that we calculate the flux as E dot ds and then integrate it. Is it clear?
Yes.
Right, because every you see that every area vector will have a different direction. So we take only this one and then this one. So this will only this all these ds will have same direction, right, as the electric field. So this simplify this thing for curved surface. And this is the same rule we apply for what are the curved surface that you see? What are the curved surface? Can you give me an example?
Spherical shape.
Yeah, so sphere or let's say cylinder,
Hmm.
let's say cone, all these things, they are curved surface, right? Plane surface, what are the plane surfaces?
Rectangle, square, circle.
Angle, yeah, not, yeah, circle is also, yes. Circle, disc. So
Yeah.
rectangle, and you have square, and then you have, yeah, so, and then you have circle, disc, you have cube, or cuboid, all those things, right? But can you tell me that what is the difference between rectangle, square, circle, disc, and cube and cuboid? So these two and all the rest ones. What is the difference between all these things?
The sides.
Yeah. So this one, rectangle, square, circle, disc, that is an open surface.
Okay.
Yeah, so this is not closed, open, right? Rectangle, square, circle, disc, these are open surface. And then you have closed surface,
Cube and
right?
cuboid.
Yeah, so cube, cuboid, and also this sphere, right? Sphere, cylinder, and all those things. right? So whenever you have an open surface, then flux is simply E dot A or integral of E dot ds, right? Whenever you have a closed surface, then this thing would be integral E dot dA, and this would be closed integral. Clear?
What does this closed mean by?
Closed meaning that your surface or your this sphere is a closed one, right? You cannot
Yeah, but
find, yes.
okay.
For example, you have a cuboid, right?
Hmm.
So all those cuboid have six surfaces and they are closing, right? You cannot find an opening in that surface.
Okay.
But let's say if you have a square. So square is a plane surface, it is an open surface, right? You can see the area, right?
Yeah.
Inside or outside, it doesn't have inside or outside, right? But for
Okay.
example, if we have a cuboid is a closed one. You have an inside and then you have outside, right? So let's say
Okay.
you have this cuboid, right? So you see that this is made up of six surfaces and they are closing each other, right?
Yes.
So in this case, if you calculate the flux, then it will be phi 1 plus phi 2 plus phi 3 plus phi 4 plus phi 5 plus phi 6, right? Due to the
Hmm.
closed surface, because we have six surfaces, right?
Yes.
So this is the thing that we have to be very careful of in this electric flux. What kind of surface is that? Or yeah, so an open surface? Is it a closed surface? Is it a plane surface? Is it a curved surface? If it is a curved surface, you use this one. If it is a plane surface, we use this one. Right?
Yes.
Okay, and that is dependent upon area, right? If the electric field is different, then there is another case. But yeah, so okay, you please note down these things, and then we will, yeah, and then we'll talk about the electric flux. Oh, we have
Okay.
already talked about it, but we'll talk about the Gauss law, right?
Done, sir.
Done. Okay, so there are lots of different questions, right? Based on this electric flux, we will do those questions together with the Gauss law, right? So let us understand this Gauss law first, and then we'll do that, right? So yeah, so let us find out the electric flux of let's say, right, this is a point charge and we are finding out the electric flux on this sphere. Right. So this is, yeah, we have this sphere and we inside that thing, we are placing a point charge. So electric field will go like this, right? It will come out radially, right? So this is R and it will come out in the direction of all those R's, right? Now, if we take, let's say we want to find out this thing, so we take a small area in this part, right, ds. So this would be in the same direction as r, right? So phi would be E dot ds, right? And then this is a closed surface, so this would be closed integral, right? Clear? Clear?
Yes, sir.
So now the angle between electric field and ds is what? That is 0, right? So this would be EDS cos 0. So this would be cos 0 is 1, so this is simply EDS, right? Now the same electric field is coming out of this surface. So at this point, 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 all these at all these points, electric field would be same, uniform. So we can take it outside, right? And this would be simply EDS, right? So now we have to just integrate this surface. So if we integrate the whole surface, what would be that thing? What would be this whole surface? With this whole surface?
The area.
Area, surface area of that sphere. So that would be 4 pi r
4
square,
pi r square.
right?
Yeah.
Now we also know the electric field magnitude, right? Because this is a point charge and at r distance, we are calculating the electric field. So what would be that electric field? Electric field due to a point charge. So this is a point charge we are calculating at r distance, right? So
K
electric field,
Q.
yes, kq by r square, right?
Hmm.
So this is kq by r square. And this is 4 pi r square. So r square will cancel. And k is how much? That is 1 by 4 pi epsilon naught. This is q and this is 4 pi. So 4 pi cancels out. So we have only q by epsilon naught. And this is where we define the Gauss, right?
Okay.
So what? Yeah, so the Gauss law states that whenever you have a closed surface, right? Whenever you have a closed surface, in closed surface, the flux is equal to the charge enclosed by epsilon, right? So in a closed surface, so in a closed surface, electric flux or magnitude of electric flux of electric flux is 1 by epsilon naught times the charge enclosed. Right. And it is written like in two ways. So it is written like E dot ds. This is Q enclosed by epsilon. And this is your flux. Right. So we'll talk about this thing and we'll do many questions in the next. But yeah, these things you already knew, right?
Yes, sir.
Okay, so yeah, we'll skip this part because yeah, other people are joining. So yeah, do you want to note down this thing, or you already knew this thing, right? So then yeah, let's stop here, and in the next class we'll do all those questions. So that